In the realm of celestial mechanics, Kepler's contributions stand out as pivotal. He built upon the foundations laid by his predecessors, ultimately solidifying three fundamental laws of planetary motion. These rules transformed our comprehension of how planets navigate their orbits around the Sun, forever altering the landscape of astrophysical study. At the heart of these revelations lies Kepler's first law, often referred to as the law of orbits. This principle asserts that planets travel in elliptical paths, with the Sun residing at one of the foci. This groundbreaking insight reshaped humanity's understanding of planetary movement, illustrating a universe far more intricate than previously imagined. Transitioning from orbits, we arrive at Kepler's second law, which introduces us to the idea of equal areas being swept out in equal times by a line drawn from the Sun to a planet. This observation mirrors the conservation of angular momentum, encapsulating the dynamic interplay between a planet's distance from the Sun and its velocity, a dance of celestial bodies bound by the laws of physics. Speaking of forces, the gravitational pull is the unseen thread that binds the Moon in its orbit around the Earth. This force is an exquisite demonstration of centripetal motion at play, underscoring the fundamental principles of orbital mechanics and the intricate balance required to maintain celestial orbits. Shifting gears, we find ourselves at the doorstep of Newton's groundbreaking revelations. He revealed that the gravitational force diminishes with distance, leading to his universal law of gravitation, a mathematical framework that quantifies the interaction between two masses based solely on their separation, weaving together a comprehensive tapestry of gravitational influence. This universal gravitational constant, a crucial component in our equations, remains steadfast across the cosmos. Its significance cannot be understated, as it allows scientists to derive reliable measurements of gravitational interactions, bridging the gap between theoretical understanding and empirical observation. In the realm of gravitational physics, the shell theorem provides fascinating insights. When considering a point mass situated outside a hollow shell, it experiences a gravitational attraction equivalent to the force exerted by the shell's mass concentrated at its core, seamlessly illustrating how mass and distance interplay in the world of gravitation. Conversely, when a point mass is situated within a hollow spherical shell, something remarkable occurs. The gravitational forces from the shell's mass cancel out, resulting in a serene absence of net gravitational force on that mass. This counterintuitive phenomenon invites us to ponder the unique gravitational properties that exist solely within spherical constructs. Delving deeper, we remember the pivotal experiment conducted by Henry Cavendish, who meticulously measured the universal gravitational constant, g. Utilizing a specialized apparatus to observe gravitational interactions, this groundbreaking experiment laid the very foundation for our understanding of gravitational forces and their densities, a true milestone in the field of physics. Now we turn our attention to the equation that governs gravitational force. This formula intricately illustrates how the acceleration due to gravity is derived from both the universal gravitational constant and the mass of the Earth. Such relationships are foundational, acting as the cornerstones upon which much of physics is built. As we ascend to greater heights, the calculation of weight becomes a nuanced endeavor, involving specific equations that recognize the changes in gravitational force with distance. This understanding reveals the diminishing grip of gravity as one moves farther from the Earth's surface, underscoring its variable nature. Gravitational potential energy emerges as a significant concept, illustrating the interplay between the work done on an object at a certain height and its resulting potential energy. This energy serves as a crucial factor in unraveling the complexities of gravitational interactions, forever linking force and distance. The changes in gravitational potential energy become paramount when lifting objects vertically. This energy shift is calculated using mass, gravitational acceleration, and height differences, emphasizing the fact that energy transitions are an inherent part of our physical reality. To analyze the gravitational force between two particles, we can employ the elegant tools of integral calculus. This advanced mathematics assists in comprehensively understanding how potential energy shifts occur as particles move in relation to one another, illustrating the dynamic nature of gravitational interactions. In a more complex world, we arrive at multi-particle systems, where the total gravitational potential energy can be expressed as the sum of energies from all unique particle pairs. This principle applies seamlessly to systems comprised of any number of particles, providing a robust framework for understanding gravitational interactions. In yet another layer of depth, we unearth the concept of energy conversion, where kinetic energy gracefully morphs into potential energy as a body rises. This elegant transformation showcases the conservation of energy at work, a fundamental tenet that resonates throughout the annals of physics. The notion of escape speed introduces a captivating idea: the minimum velocity required for an object to break free from a planet's gravitational clutches. This threshold varies depending on the unique characteristics of each celestial body, adding an intriguing dimension to our understanding of motion in space. When projecting a body from an elevated position, it's crucial to adjust the escape speed to accommodate the increased distance from the planet center. This adjustment becomes essential for comprehending the complexities of satellite dynamics and the forces at play in space. We now circle back to the Moon, a celestial body whose stable orbit is maintained by the centripetal force provided by the gravitational attraction between the Earth and the Moon. This fundamental principle lies at the heart of satellite mechanics, revealing the delicate balance necessary for orbital stability. Examining the kinetic and potential energy of the Moon enables us to calculate its total energy in orbit, which often manifests as a negative value. This concept is vital for grasping the stability of satellite orbits and the forces that keep them in their respective paths. As we explore further, we find ourselves gazing at Kepler's third law, which reveals a profound relationship. The square of a satellite's orbital period is proportionate to the cube of its orbital radius. This fundamental law serves as a cornerstone in celestial mechanics and is essential for crafting effective satellite designs. Geostationary satellites are a marvel of engineering, designed to maintain a fixed position relative to the Earth's surface. Their synchronization with Earth's rotation makes them indispensable for telecommunications, providing continuous coverage over specific regions, a true testament to human ingenuity. In India, the Indian Space Research Organisation, or ISRO, operates a constellation of geostationary satellites under the INSAT program. These satellites play a critical role in addressing essential needs across meteorology, telecommunications, and broadcasting, enriching the lives of millions. Sun-synchronous satellites offer another layer of sophistication, as their orbits enable them to pass over the same point on Earth at the same local solar time each day. This consistency is invaluable for applications such as remote sensing and environmental monitoring, highlighting the innovative capabilities of modern space technology. While freefall is often associated with satellites, it is a universal principle. Any object falling freely under gravity, devoid of resistance, will experience a similar sensation of weightlessness. This profound principle transcends mere theory, applying universally to a variety of freely falling bodies. Consider a satellite in orbit around the Earth. It exists in a state of freefall, moving tangentially at high velocity, perpetually missing the Earth due to that same speed. This creates a sensation of weightlessness for everyone aboard, a remarkable phenomenon that captivates our understanding of gravitational dynamics. This concept of weightlessness becomes palpable when considering the experiences of cosmonauts aboard manned satellites. Although they are subjected to gravity, they find themselves in a continuous state of freefall, an extraordinary environment that allows them to experience a sense of zero gravity unlike anything else.